Yes, okay, here we are. So I'm Susanna Vergani. I work at Paris Observatory, and I really thank the organizer for having invited me here to talk to you about a bit about the optical infrared follow-up of gravitational wave events and of transient sources. So I want to start. Yes, to show a non-exhaustive panorama of the alert providers that we have or we will have in the future years. I will do electromagnetic, gravitational wave and neutrino alert providers. These here you can see from radio to gamma rays, different facilities that will provide us with a lot of alerts to be follow up in the optical and near infrared. And also from the gravitational wave, we will have a different frequency that will be covered in the future. And for optical and near infrared, of course, we are much more interested at the moment of the alerts from LIGO, Virgo, Cagra, and in the future for Einstein Telescope and Cosmic Explorers. But also, as you heard a lot today, there will be also alert very interested to be following the optical and near infrared by LISA, for example. There will be also a lot of neutrino detector operating in the next years, and in particular for what we're interested most, the providers are the IceCube, Chemtranet, and in the future IceCube Gen 2, anyway, new improved facilities, and there may be other to come, I don't know, but this is just to give you an idea of the large amount of facilities that will provide us alert in different frequencies and in different messages, and all of that really would be interested to follow them in the optical and in the near infrared. So I will first focus on the electromagnetic ones, and in particular on the future with the LSST on Vera Rubin, and then also of the alert from space, so mostly in the gamma rays and soft and hard X-rays like SWIFT, SVOM, and ISTAN probe that are operating nowadays. So why it is interesting to follow up in the optical and near infrared these alerts coming from these different providers. What do we want to do with the optical and near infrared follow-up? We want to study the time evolution, so to have the light curve, the optical and infrared light curves, the spectra, so to study the spectral characteristic of these transients and their evolution in time. And we want to determine the distance, so the redshift through the spectroscopy usually, and study those galaxy properties. These are the goals of the main goals of the optical and near infrared follow-up observation of transient and gravitational wave, on transient, electromagnetic transients. And with such information, with such observation, what we can do. So first of all, we can answer to the question, what are we observing? So to identify the kind of transient that we are observing, how is it the light that we are observing is emitted? So what are the physical processes that are producing the photons that we are detecting? And understand where do they come from? So what are the progenitors, the stellar story before them? And if there are some genes that are really giving the energy, providing the energy for the transit that we are detecting. So to answer this question, optical near infrared follow-up is observation are really key. So how do we want to do this optical and near infrared follow-up observation of transient sources of electromagnetic transient alerts? First of all, in most of cases, I would say yes, really most of cases, what is important is to react extremely rapidly from the alert. So we need facilities that are able to point the localization of this alert very, very quickly, so to be able to follow the entire evolution of the light curves and also the spectral evolution since the first steps of these transients. And also another thing that is extremely important is the synergy at different wavelengths. So the optical and near infrared follow-up, that is maybe the one that is the most immediate to think about because we are used historically to optical frequencies much more than other frequencies. It's just a part of the story, and to answer the question that we had before on the presentation, we really need a multi-wavelength synergy, multi-frequency synergy. And also, as we all now know, the other important part of the story now is also the multi-messenger synergies, if any. So let's start from the transient that are identified in the optical near infrared. So in this case, Vera Rubin and nowadays his predecessor, ZTF. I want to stress some things here. I will give you not detailed information of what kind of transit, but at least to give you some ideas of what is going on. So in the last decade, we really saw a blooming of new transient appearing in the optical near infrared sky. Here, there are some of them mentioned, like tidal disruption event, orphan afterglows, and these luminous fast blue optical transients that are all newly been detected in the last decades. I saw them here classified in their brightness in function of the, let's say, duration of their maximum peak. So as you can see, you have here the gamma ray bursts that are the brightest, and also the one that are bright, very bright, but for a short amount of time. And then you have here a kind of continuum with orphan afterglow, tidal disruption event. And here are the classical, say, most classical supernovae, with also the new class of superluminous supernovae that are brightest, as you can see. And then we see here the apparition, that they appear new phenomena like the luminous fast blue optical transient here in yellow, that are kind of extending this supernova regime towards brighter and shorter lasting events. So I just want to focus a bit on this F-bot, just to give you some example what are the information that we can collect in the optical and near infrared and why they are important. Here is this idea of a very rapid increase of luminosity. Thanks to the service like ZTF, we have deep limits before the peak that really tells us that the rise is very rapid. And then we have also a fast decay compared to other kind of supernovae that we could imagine to compare this F-bot with. So now there are detection of some of them, and those are the characteristics and the questions that are still open to understand what they are, in fact. So they are too luminous, too fast, but too slow to be other categories of objects. So we have some questions marked on that, and also maybe they are not all the same thing. Maybe they are different things, some more going towards TDE, other less, and so on. Another important thing, you can see, you can use this, your optical information to really try to single out the population compared to other kind of population. And this is another way of seeing what we saw before, and maybe more clearly comparing the F-bot with the other kind of supernovae, or these are kind of supernovae, okay? And you see that they really cover a separate space, except for one of them that you see here. And for example, at the beginning, they were thought to be associated with core collapse supernovae with broad line, like the one that are associated with gamma ray burst. And in fact, no, except for this one, but they do not occupy the same region. Also, they have another characteristic that their spectra is almost featureless. And this is also something that we learn from the optical near infrared follow-up. So here is the time series, so the time, the spectral evolution in time of one of these F-bot, and in fact, compared to other class of supernovae that we suspected to be linked with such phenomena, we see that is almost featureless. We would expect some broad lines that we don't see, and so it's also here is another example where we can also cover the ultraviolet part, but it's kind of a black body without some features that could indicate, for example, circumstellar material interaction or broadline supernovae and so on. So this is all this information together are really very important to build the picture of this phenomenon, try to understand what are the progenitor stars that gives rise to these things, what they are, and also, as you can see, I also join some other characteristics that come to Adam frequencies that are also very important to understand the nature of what we are seeing. Then I wanted to spend a few words on the fact that we can also learn a lot studying the host galaxy of this transient object in the optical. And this is something that we did a lot in the past for gamma ray bursts, for example, but not only. For example, the property of those galaxies of gamma ray bursts that are associated, the long ones that are associated with the massive stars, are very different from the one of other transients that are also associated with massive stars that can be type 1c supernovae. They have completely different masses, metallicity, and so on. So the fact that they found in different galaxies, they can tell us that they need some specific characteristic. So the stellar population that form these transient events has to have some specific characteristic that differentiate such transients compared to other kind of classes of transients. So here in yellow, there is an example of this F-bot compared with the properties of superluminous supernovae in blue and of field galaxies in black. So you can see that the properties are not so extreme in terms, for example, of stellar masses or metallicities as the galaxies of superluminous supernovae, but they are very much they are more extreme in concerning the star formation. So this is the star formation compared to the mass of the galaxy, and this is the star formation of the galaxy itself. Those are more similar to the host gamma ray burst, for example. Then let's talk a bit about the future. So with the LSST, what we will have. So LSST will be able to scan the sky in much deeper, so fainter, detecting fainter object and be far in the volume of the universe. So we will have maybe new class of transients identified going fainter that we don't see nowadays. And for sure, we will explore the transient that we know up to higher redshift. All this will be very difficult to follow up in the optical and infrared. Why? Because here if we are taking advantage of the fact that they go fainter. But in fact, it's very difficult to have facilities to do the follow-up in optical and infrared at magnitude as faint as those as probed by LSST and the Vera-Rubin. So, for example, if you want to cover magnitude of the order of the 24, 25, and so on in the optical and do spectroscopy on this regime. So to go down to that magnitude, optical magnitude in photometry, we need to go to 8-meter class telescopes, and the spectroscopy is not possible to be done even with 8-meter class telescope. We have to go to space. So of course we can't use such large facility to follow up a large amount of transients, maybe for some of them, but for sure not for all the ones that will be detected by LSST. On the other hand, if we consider the fact that LSST will be very sensitive, we can also use this aspect to have more information on the transients that are bright peak, so the transients that are nowadays detected also by ZTF, because we can have information on their behavior before the peak, and also maybe at what happened in a later time. So for sure, this synergy between LSST and other kind of surveys that are not as sensitive as LSST will be very, very important. We will have many alerts from LSST, and this also makes it very difficult, the optical and near-infrared follow-up, because we don't have the amount of time at the telescope that we would like to follow up all these alerts and to identify what is the transient that we are looking at, and to determine the properties and so on. To this purpose, facilities that are dedicated to transient spectroscopy will be extremely helpful, because spectroscopy is a direct way to understand or to discriminate one kind of class of transient from another. So if the object that the LSST detected was a type 2b supernova or an orphan afterglow or something else. And I give you here an example of such facility that is SOX, that will go at Isola Silia very soon, that is really dedicated to transient spectroscopy. but also is sure that we have to build up a coordination of all the information that we will collect in for this kind of observations. And this is something that ACME is, let's say, is one of the goals of ACME, to build such interconnection between different community for data sharing and easy, let's say, to make information together in an easier way and open to as most as possible. Also, I want to stress a last thing about LSST, that the cadence at which LSST scan the skies at different wavelength is really not optimal for such kind of transients. So now is a compromise between different science cases. It's much better to what it was thought originally, because it was not at all skewed to transient sky, but still is really not optimistic for this kind of study. So it will not be very, very easy to learn how we will work within the LSST data and alerts. Then I want to tell you a bit about gamma ray burst. So the optical and near infrared follow-up of gamma ray burst detected by space satellites. So as said before, gamma ray bursts are extremely bright. This is a very good point. The bad point is that extremely bright only for a small time. So with GRBs, we are really running against time. So there, the strategy of observation is really very precise, and we have to go quickly. So we have the alert from the satellites. If the alert is we have two kinds of detection, let's say. We have detection from space only in gamma rays, where the localization is not precise at all. And the other detection, especially for these two satellites, that are able to repoint with their X-ray and ultraviolet or visible instrument or board, and provide much more precise localization. So in case we don't have precise localization, or we drop it, or we have some robotic telescope that reacts immediately after seconds to the alert, and try to scan the error region of the gamma rays to find the counterpart and give a precise localization. In case we have already a kind of a good localization from space, we can immediately, automatically, without human intervention, trigger large telescopes, interrupting the observation that are ongoing. This is what we do with VLT, so as to be really on target and do photometry spectroscopy in few minutes. The record, I think it's 10 minutes, something like that. So, of course, when we are in such cases, we can do a lot of science more. But we maybe also not be so lucky enough and not be night at VLT. And in this case, if it is, let's say, during the day, we can do target of opportunity observation to follow up the light curve with other telescope, and then to activate the spectroscopy with VLT later on. So we are talking about seconds, or at most a day, but then it's gone. It's especially for spectroscopy, it's really gone. So why we are interested to do this spectroscopy of gamma ray burst? I want just to briefly mention that for the gamma ray burst from collapsar, those that are associated with star formation, we can detect it up to the very high redshift, and thanks to the fact that they are so bright, we can study the host galaxy properties, so galaxy at very high redshift. We can study them through their ISM, through the absorption lines. And so we have a lot of information also for galaxies. Here, there is supposed to be a galaxy, but it's so faint that it is not detected even with HST. Instead, with 1 hour of observation of a gamma ray burst afterglow spectrum, we have a lot of information on the properties of this galaxy. I show you here an example, redshift 6.3, where all these absorption lines come from the metals in the ISM. So we have information on the abundance of oxygen, silicon, iron, carbon, a lot of elements of the host galaxy ISM, and we can use them to study the nucleosynthetic patterns in that galaxy, especially at high redshift, to see if we have some special nucleosynthesis ongoing for some kind of first population of stars and so on. the same, not the same, but also the gamma ray burst from mergers of compact objects that are what we usually call short gamma ray burst can be used to study the enrichment of the universe through the kilonovae that are associated to them, so that we can study the air process nucleosynthesis ongoing in kilonovae. So this is the example of the event associated with the GW170A17. And I show you here the sequence of spectra obtained with VLT X-shooter. And studying the spectrum, we have, depending on the phases that we are studying of the spectrum, we have there have been claims of detection of strontium, yttrium, lanthanides, tellurium, if we study the radar peaks and the radar peak evolution and so on. Those studies are particularly interesting, of course, new, but extremely difficult because they depend also on the uncertain models of the kilonova emission and on the let's say on the not available or incomplete atomic data for such heavy element transition. So it's a really, really difficult exercise, but very challenging, but very interesting. And now we also we are also able to perform this follow-up with large telescope from space, thanks to the Webb. And so even if we didn't have any other kilonovae from associated to gravitational wave event, we have them from gamma ray burst, just without the GW detection, but from gamma ray burst, we can go and look for the presence of kilonovae associated to them. And this is what we did from space with JWST. For this burst here, and this is the kilonova with a probable identification of tellurium, still debated, and then the analysis is still ongoing. So I want also to stress that with these two guys, we can now extend the detection of transients from the space to lower frequency. So we are going to cover kind of the X-ray domain for the alert. And this is particularly interesting because it opens a field of the so-called fast X-ray transients, and also is very interesting in the field of gamma ray bursts themselves, because if we plot here the peak energy of gamma ray bursts in function of their isotropic energy, we have here the two classes of long and short gamma ray bursts. But we have some gamma ray bursts that, for example, belong to this category of long gamma ray bursts associated with collapse stars, but instead of having luminosity of 10 to the 51, 52, and so on, they have luminosity of like 3 or 4 orders less. So these are what we call low luminosity gamma ray bursts. And it is still not clear if they belong to the same class, let's say, of phenomena, the same processes, and how they are, why they are so low luminous in gamma rays, not as luminous as the other. And also we can explore the parameter space of transients, energetic transient, relativistic transient, with peak energy that are much lower to what we usually detect with current satellites. And these are what we call X-ray flashes, or X-ray flare as you want. And so with the E peak that is less than the one of gamma ray burst. And for example, this could be gamma ray burst C slightly off axis, or gamma ray burst with slower ejecta, and so their peak is not in the gamma rays, but is not as high as the gamma ray burst, but is much fainter. And really, SVOM and EP are populating this parameter space, and it will be really interesting with the optical near infrared follow-up, also of their host galaxy, to see if they are the same properties of the classical gamma ray burst in other terms. So then I will conclude my talk speaking about the perspective of optical and near-infrared follow-up of the next generation gravitational wave event, gravitational wave detectors, so Einstein Telescope and Cosmic Explorer. And here I show you of course, of the electromagnetic counterpart of the binary neutron star and neutron star black hole event detected by such interferometers. And those counterparts, as you know, are gamma ray burst, they are afterglow or off-axis afterglow, and the kilonovae. So in this plot, you can see how with, for example, ET, we can extend the volume of the universe in which we will detect binary neutron star mergers. So I will anticipate that, and you can see beyond, that it's true that we can extend this volume, but please beware that beyond redshift of about 0.5, the way to do multi-messenger astrophysics is through gamma ray burst, on-axis gamma ray burst detected by the satellite. So it's extremely important to have satellites that are capable to identify, to detect and localize gamma ray burst at the epoch where ET will be operational. And so in this case, we will have the gamma ray burst identified on axis, and with the follow-up in the optical and near infrared that I showed you just before. So then here on the right, you have the numbers, the expected numbers for binary neutron star detections per year in function of redshift and in function of their localization. So as you can see, if we take event with less than 100 degrees squared localization, you can see that we are limited to the low redshift regime. And here, this is for ET alone, and this is for ET with Cosmic Explorer. And you can see the really improved precision on the localization in this configuration of coordination between the two interferometers. So we will have up to redshift 1 a lot of events with localization better than 10 degrees squared. So it becomes to be really interesting also at up to redshift intermediate or high redshift to follow up these sources. Okay, here I really show you the challenges of the optical and near infrared observation of the counterparts. And those plots that I will show you are, you can find them in the ET Blue Book that is now on the archive. And they're being done under the Division 4 of the ET Observing Science Board that I co-coordinated with Giancarlo Ghirlanda and Drew Levin. So here you can see on the left the prediction of the brightness of the kilonovae associated with BNS detected by ET. You can see that, so for different configuration and different theoretical model behind, but the message is one, most of them will be extremely faint. In the optical, you can see from 24 to 25 to 26 at the peak. On the right, you have the prediction of the brightness of the orphan afterglows. So, of the afterglows. Here, of course, when you have this peak, high peak there, here you have behind the optical light curve overplotted. So here are the cases on axis, and those ones are the cases where we have only the off-axis afterglows, and the optical curves are the green ones. So as you can see, the most probable is to have event extremely faint or synoptical and at peaking at very late times. So these imply that we have really to think a lot about our strategy of follow-up, and they will not be so easy because of the faintness and because of the need of monitoring for a long time the orphan after the off-axis afterglow of these sources. So, how we can detect such counterparts for kilonovae, as you saw 2 days ago in the talk of my student Sofia Bisero, we have Vera Rubin that we can detect most of them up to redshift, let's say 0.4. So here is where I tell you that beyond 0.5 it's is dead. We will need to rely on axis gamma ray burst. And here you can see in green the one for which we can have a spectroscopy for this new generation of spectrograph like the WST that Sophia showed you 2 days ago. So the other way to try to do such search is through galaxy targeted searches, as we did for the event of 2017. But as you can see here, as Sophia showed you, as soon as you go to to redshift that are not the local universe, the number of galaxies in the co-moving error volume of the ET detection becomes very high, or the order of thousands of tens of thousands. So also for this, you need specific instruments, and we have the time really to push for this instrument to be built, to be operational together with ET. I will just plot my last two slides that are the specifications, the, let's say, requirements for the specification for the facility that we need to perform electromagnetic studies. And in particular here, I focus on the optical and near-infrared facilities to perform multi-messenger studies of BNS detected by the next generation interferometers. So you can see here the field of view, the sensitivity, spectral ranges, resolution, and delays of observations to search for the electromagnetic counterpart and to characterize the electromagnetic counterparts. This is for the off-axis afterglow, so we should go very deep, as you can see here. And I stress again that our searches can also last years, also in the optical. And then here is for the kilonova search and characterization. So here we can be a little less conservative in magnitude for the search, so less strict. And also, we don't need to react really in the first hour, but you can wait for 1 day or something like that in the optical near infrared. In the ultraviolet, we need to go soon because the ultraviolet peaks very early. And you can find in the blue book this table and also the same tables. We made the same tables also for the other frequencies. So for the X-ray facilities, gamma ray facilities, and radio facilities as well. And on this, I finish. Thanks a lot for your attention, and I'm happy to take your questions.
Are there questions?
Hi, thanks for a really nice talk. So when you said LSST cadence will be bad for these types of transients, I heard something like 4 days. Is that the compromise or is that the bad case?
The compromise.
Oh, okay.
I mean, it's better than the bad case.
What was the bad case?
Not ideal because we will need a monitoring much closer in time. So to revisit more time that what will be done. But okay, there are a lot of science cases in LSST, so of course it's a compromise.
Yeah. And if I could ask one more, so would you say that with the orphan afterglows, of course, it'll take might take all years for the signal to show up. So are we currently looking? I guess we don't have sensitivity yet. Are we currently looking in optical for the NSBH signals years after or months after they've? Like how have optical follow-ups been for NSBH mergers, for instance?
So to do this kind of searches now, you need, follow-up searches, you would need triggers. So for the moment, we don't have, from the gravitational wave, we don't have any triggers that is well localized enough to make this long-time search worth it. On the other end, you can expect to have this detection made, for example, LSST, scanning the sky, can find such things independently from the gravitational wave event. The problem is how to recognize that they are those, because you will see a very slow rise that you can maybe think associated to other kind of transit and so on. And as you see, the magnitude that we expect are really very faint. So I think that maybe with some ELT or JWST spectroscopy, we could do the spectra of such kind of sources. So of course you cannot use JWST or ELT to do the spectra of I don't know, 100s of such sources, but maybe for some of them yes, and then you can see if you are looking at off-axis afterglow.
There was one more question.
Yeah, thank you for the very nice talk. Just curious, so what are the underlying assumptions for the kilonova predictions in terms of like mass ejection, composition, and like population statistics for the underlying binaries?
There were two there. So one was the one based simply on 2000 on the event on the kilonova 2017, and the other don't remember what the prescription. Maybe Sophia, you remember the yes that
There
they
were
used.
Yeah, they use BLH and APR for equation of states and Gaussian and uniform mass distributions of neutron stars. Yeah.
There are the references are in the paper of Lofredo et al. 2025 because it's been accepted I think or now, so in the last week or so. So you have the reference there of all the model they use.
Thanks a lot. So we have to move on. Maybe other questions for the coffee break. Okay. Thanks a lot, Susanna.